Thank you for taking the time to come and listen to the talk that I will be giving at the FME World Tour 2021, titled Magic Tricks for Taming Wild External Systems Using SSH Tunnels and High Volume HTTP Calls. My name is Dr. John Stanger. I work for Spatial Partners based in Melbourne, in Australia, and I like to joke that my job title is a literal wizard, as while what I normally do is as a senior solution architect. Often some of the solutions that I will propose seem so ridiculous and unexpected that they are effectively like magic. And so as a result, I like to call myself a wizard. So what is the real purpose of this particular talk? What I'm wanting to talk about in this is covering some of the more niche limitations that FME has, because despite being a broad tool with some amazing properties for being able to facilitate automation and integrations, there are occasional cases where you will find that FME is unable to rise to the challenge that the big wild world poses to it. And two of these areas are where I'm going to be covering today. So first is the inability to access certain very secure data that is locked behind firewalls on private networks, which prevents things like FME server from being able to access it from external network. And the next one is covering cases where there might be very slow performance of executing your workbench due to sending large volumes of HTTP requests. Okay, so I've got SSH tunnels as the first thing up, where we're going to be doing some digital sapping for secure profits. So there are occasional cases where you'll have sensitive and secure data that can present significant cybersecurity risks to open up and allow external connections to that data source. So how do you let this dangerous beast out of its data out of its cage? So there are a number of cases where on-prem databases or GIS services that host sensitive or secure data that will present you with significant headaches or challenges in terms of trying to connect to it for, say, providing an ETL pipeline or automation. And some data is so sensitive that the potential impact of the risk of that data being compromised is so high that it is infeasible to actually allow that data to be exposed on the public network. And so this then forces the on-prem hosting of FME server, which is a valid option and approach to take this. However, that can potentially limit connections then for FME for being able to access the external network by being blocked by this very closed network, or it can actually result in a poor utilization of that particular automation infrastructure. And so potentially the challenge that we're going to try and get around here is getting around needing to open firewall ports because that increases your cybersecurity risk by exposing your very secure data source to potential public attack. So our solution to this, we believe we can get away maybe with using SSH tunnels, which can provide an encrypted connection path to something that is referred to as a bastion or jump server, which acts as an intermediate, usually at the network boundary. And then with careful configuration of that bastion server, you can basically narrowly scope what possible connections are allowed. So therefore only accepting connections that are made with a secure certificate over this secure protocol from the known FME server, therefore absolutely minimizing and locking down the connections to the secure data source. So how do you go about doing this? Well, I wish I could tell you that there was a nice, easy, standard drop-in way to do so, but unfortunately it gets a little complicated, but still doable. So what we will do is we'll take advantage of the OpenSSH product, which is available both on Windows and Linux, so therefore can be used alongside any version of FME server that you're choosing to use. And then we utilize a startup and shutdown Python script to basically set up a process that is executing the SSH client to create a tunnel before the FME workbench runs, and then even if the workbench fails, the shutdown script will run and close that connection, and therefore allowing that port to be reused by future workbenches safely. And so this works actually fairly effectively, and sometimes just requires a little bit of finagling to be able to put things out, set things up correctly in terms of host keys and things like this. So the primary example that we've actually used this for is we were actually asked to create a ETL pipeline to be able to sync multiple on-premise financial databases that actually had a handful of different schemas to a single cloud source. And this posed a bit of a challenge because with the different schemas and the different ways of treating things, we actually decided that possibly taking advantage of FME might actually be a great way to get around a long and lengthy and difficult ETL sort of scoping and design process. But this meant that now we had to figure out how we were going to get FME in one place to talk to many, many different sites and be able to extract that data. So what we ended up doing is we got each of the individual databases, so each of the servers that are hosted on-prem to sync, basically create a standing tunnel to the Bastion server located out, in this case, out in the wild. And then this Bastion server only accepted connections from those different databases and only from the FME server that we were using. And then we used FME server to then reach in and create a connection. So it was actually able to create multiple parallel tunnels to each of the different servers, running multiple workbenches at the same time. And then that allowed us to synchronize that data to the cloud application, bringing all their financial data together into one place in one single schema. So another example where we didn't quite need to use this because we found a way around by modifying the underlying infrastructure was that there are certain cases that we have encountered where some of the GIS data that's being stored by an organization either has commercial sensitivity or represents something like personal data that needs to be kept very secure and private. And so while we managed to get around this, we were tasked with combining some of this data with other data from services that were required a cloud connection to produce a payload. And so this could have been circumvented, like the issue could have been resolved by using the exact same pattern to be able to get the secure data server to basically push out, expose the port for access, then allow FME to access it, and then based on whether or not the user that's requesting the data is allowed to see that private data, is then able to extract that and package it up together with the other cloud services. All right, so now we're getting on to some really exciting speed things. So this is using asynchronous HTTP. And so this is all about promises and knowing the right time to wait. So we have found from our experience that if you're making very high volumes of HTTP calls, this can result in workbenches wasting up to 95% of their engine time waiting for network traffic. So if you've ever hated having to wait in line for a roller coaster, imagine your features waiting their turn to finally get their chance to scream around on the net. So the challenge that we were facing is that in some cases we've been asked to send thousands of HTTP calls for a single workbench execution, and sometimes you can't avoid this, often when you don't actually have control over the destination API that you're communicating with, because it's part of a third party. And so unfortunately, FME's native HTTP caller only supports making a single connection at a time, and this is a very reasonable limitation because you do not want to abuse APIs out on the web, because particularly for commercial or for open source hosted ones, making thousands and thousands of connections simultaneously can cause a server to crash, and therefore it is quite reasonable for this limitation to exist. However, in certain use cases, it is a frustrating limitation. And so as an example of what motivated us to sort of seek a solution around this, we have an example here of making 1,000 requests, simulating web scraping, bringing in from a standard web server, approximately 100 kilobytes per payload, and this took about 56 seconds. Now, these times should be treated as relative, not absolute, but they have all been executed on the same machine with the same setup. And so a similar kind of thing is, say, interacting with a commercial map API. In this case, we're only retrieving a single feature at a time, and so it's only 600 bytes worth of data being transferred. It's a little slower in responding, and that ended up taking, for 1,000 features, bringing that in about 310 seconds. And then the thing that really motivated us is that at one point we needed to update a single attribute in all the features that were being hosted on a particular cloud map service. And this required us to then make effectively 70,000 plus HTTP post requests, which took the workbench over 6 hours to complete. Now, do you think it spent 6 hours actually doing compute time, or did it actually spend 6 hours just waiting for network traffic? You know the answer. So this brings us to the discussion of a CPU-bound process versus a network-bound process. So if your process requires a lot of thinking power, then you need to use multi-threading and, you need to use parallel processing. Whereas if the thing that you're trying to achieve simply is dependent on a lot of network traffic and therefore depends on the speed of the machines on the network responding and also on the capacity of the network to transfer data, then you can actually deal with this particular situation by using multiple threads rather than multiple processes. And so the way we deal with this, which is common if anyone's familiar with JavaScript, is utilizing the promise asynchronous code pattern. So this is effectively the idea that you request for something to happen with your code, and what you get back instead of the response, which would be a synchronous pattern, is you get back a promise, which is a digital object that when the response arrives will then resolve to that response. And so that allows the CPU to then move on and do work elsewhere, such as on parallel requests, and then come back when the response is ready. And so the other little piece of technology that we needed to take advantage of here to be able to make this a reality for us was something that Spatial Partners itself has actually developed, which is a technique of basically packing in a set of Python code into an FME transformer so that it is using all the power of FME's native UI, but actually has everything embedded into a single FMX transformer, allowing it to be distributed over the FME hub without needing to have any secondary files or extra libraries or anything like that installed. So much, much easier. So announcement, hurrah! So the asynchronous HTTP caller is now available on the FME hub. So we have used the Python 3 standard libraries of async.io features and requests, all included in your standard FME install, as long as you're using Python 3 compatibility. So everything going back for the last couple of years, those versions of FME should have no trouble working with this. And this is all packaged into a single FMX file under the MIT open source license, making it very easy to work with in the FME ecosystem and work with your workbenches. And it also mimics the existing HTTP caller interface to make it fairly plug and play and familiar for existing users. So the beta release is now available. It is a beta release, so please tell me whether or not it's actually any good. Highlight for me any issues. Do test extensively before putting it into production. In fact, I would not recommend putting it into production quite yet, but hey, that's your choice. But if you type AsyncHTTPCaller into your FME workbench right now, you should be able to get this transformer available for you. So let's see whether or not it solves our problem. So a web mapping product that Spatial Partners is quite fond of and frequently recommends is GIS Cloud. And like many other web-based GIS services, it's possible through their API to get features and do this in bulk, get large pages worth of features, and that's good. That's relatively efficient. However, if we're going to update the feature, their API, quite sensibly, requires us to specify which feature we wish to update. And this means that we can only do that one at a time via their API. So benchmarking it, as we'd seen earlier on the slide, if we're using the HTTP caller standard with FME, this will take about 310 seconds, which will spend almost 100% of its time just waiting for servers to respond, not really doing any actual work. Whereas, if we bump this up so that with the async HTTP caller, we configure it to use 20 parallel threads, what we will get is for the same request for 1,000 features, we can bring that down to 55 seconds, and now we're only spending a third of our time waiting for network traffic. And if we bump that all the way up to 35 threads, this means there's always 35 parallel requests occurring at the same time. This drops that time down to a mere 30 seconds, now 1/10 of the time, so a 10 times speed improvement. So another example where we ended up having to use this was in another ETL pipeline that we did to take data from a fairly complex data model from the client database and post it up to another web application to expose it. And this, unfortunately, the web application, again, only supported a single feature per post request. So being a third-party API, we could not modify this. But the nature of the complex data model of the data that we were syncing from required us to then, when we calculated it out, we would be expecting a volume of around 150,000 post requests per day to be able to maintain that synchronization for 1 day worth of data. So this posed a bit of a problem because when we looked at how quickly it was going to respond, we were estimating it was going to take more than a day to complete the synchronization of 1 day's worth of data. Not ideal. So when we brought the async HTTP caller in, it turned out that this remote service was able to accommodate a fairly high volume of parallel requests. And so we were able to bring that from 1 day down to approximately an hour per day to complete the full synchronization process, which was much, much better. So another small example, which again, if you're going to do this, please be very careful about abusing particularly public services, because they are quite often not that highly funded, and so it can be very bad if you're pushing out very large numbers of simultaneous requests, because that may impede the service being provided by that server. However, we could bulk download all the collections or a set of collections from WFS service or a WMS service. And so taking a quick benchmark against a publicly available WFS service, getting approximately 20 megabytes worth of data. If we're doing this with FME's native transformer, we're spending about 80% of the time idle, taking 20 seconds. We can halve that by using the async HTTP caller to increase the number of threads. But you can see here as well that the speed increases will decrease, probably because in this case, the server is actually throttling us because we're making too many simultaneous requests. A quick example of how one might use this for web scraping or crawling, or if we're doing high volume geocoding with a service that isn't supported by FME's native transformers. This would result, if we're getting Spatial Partner's website, we can see that it normally takes about a minute to be able to get 1,000 GET requests and spending over 80% of its time idle. However, if we bring that up to 20 or 35 threads to make those parallel connections, then we can bring that all the way down to about 14 seconds, spending no time actually idle with the CPU. And lastly, even the mighty FME server API does have some edge cases that we have encountered that, particularly if you need to do some kind of advanced filtering on some of their endpoints. So if you're wanting to automate the automator, then there might be cases where you have to make high volume HTTP calls. And so this might be a case, for example, of selectively purging logs from the server when, based on the workbench properties, or if you're needing to bulk retrieve multiple workbench results from at the end of their execution, or potentially consolidation of multiple log files. So in conclusion, secure access to on-prem data is possible, but it's not necessarily easy. And now you have the ability to bring your HTTP calls into hyperspeed, but please make your HTTP calls responsibly. Thank you very much.